Welcome back for yet another thrilling installment of our calculus journey. We have arrived at the coveted curve sketching chapter, which is really Algebra 2 and pre-calculus on steroids, for lack of a better analogy. But let's jump into it. So extreme value. So a lot of the information here, before we actually even get to curve sketching itself and its calculus-related applications, is prefaced by foundational vocabulary. So we have extreme values, aka what we call extrema, which are the maximum and minimum values of a function. And if there's only one point, we would refer to that as extremum. So if we were to define extreme values on an interval, let f of x be a function on an interval I, and let L, A be an element of I, so some arbitrary value inside of our interval. We say that its output is an absolute minimum if f of a is less than or equal to f of x for all x that are contained in this interval. And your intuition should be kicking here, because in order for that value to be an absolute maximum, that would mean that f of a is greater than or equal to the rest of the function outputs for all inputs inside of that interval. Now, rhetorically, does every function necessarily have a maximum or minimum value? That answer is no. Easy one to think about is our OG algebra 1 function, f of x equals x, right? It's constantly increasing towards positive infinity and constantly decreasing towards negative infinity, so it theoretically becomes impossible to define a maximum or min value. Typically, we say that we examine maximum and minimum values on functions that have at least a degree of at least 2 or more. Let's take a look at some graphs and talk about discontinuities, just to refresh what we had done during our limits exploration. Okay. Let's say we have a graph here, A, B, C. It's a little rough. All right, we can say right there. Or we can put a value here, and let's say 1, 2, 3. Okay. Don't get it twisted. Right, we're not talking about limits here, we're talking about continuity. So we can clearly see that this function is undefined at x equals b, which is roughly 3. So we would describe this with a removable discontinuity with no max value on A to C. it becomes theoretically impossible, right? Because we can seemingly get infinitely closer to this hole without never touching it. So there becomes no max value. Now on the flip side, let's say we had something like this. Here, we can say, and we're assuming that this is an open interval, but we can say that this function is continuous with no max or min value on A, B. Now, the reason why we can say continuous here, even though there's a hole, and that hole is supposed to be on A, is because we're not using closed bounds here, right? We're keeping our bounds open. And our final graph, which should be very obvious, we don't need these anymore. Is where we have an obvious minimum value and an obvious maximum value. So we can say that this is a continuous function with a max and a min on some closed interval A to B. Now, notice, right, we've been working with continuity through limits. We've been able to determine the coordinates of maximum and minimum values through our knowledge of derivatives, or at least the first derivative. So let's talk about how do we verify or even prove that there exists extremum on an interval. Right, so theorem 1, or I'll just call this theorem, existence of extrema on a closed interval. Which is a continuous function f of x on a closed interval AB. Takes on both a max and min value on AB. And I know you might be sitting there watching this video and saying, well, didn't you say before that f of x equal Sx does not have a maximum or a minimum value? I did. However, I did not say that we had to find it within a particular interval. Okay? This is a key piece of this theorem. We must have a closed defined interval. So let's branch off of our extreme values and talk about local extrema. So we can define a local min at x equals c if f of c is the minimum value of f on some open interval containing C, right? And notice how key difference between this and our absolute minimum, absolute maximum intervals. Open interval, rewind time, closed interval. Okay. When the interval is open, we don't know what the behavior is, or we might know what the behavior is, but we're not necessarily considering the behavior of the function and its subsequent outputs outside of that particular interval. And to spare me having to erase and rewrite, we would define a point to be a local maximum at x equals c if f of c is the maximum value of f on some open interval containing c. In my previous, or my final graph from before, I made a mention of this, but I will redraw it. So graphically we can see that we have local max, one local max, and two local mins. I had said that we were able to utilize at this point derivatives to help us identify what those coordinates are. And the reason why we can apply or utilize this concept of derivatives, oh wow, completely missed that point. Let's move this up a little bit. It is apparent that in blue our extrema have horizontal tangent lines at that point. So if we were to derive a function, we know that the slope with the derivative would be equal to 0. And that's where we're going to take a 30-second timeout and pick up in part 2 of this video.